Hello, 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 hello. Okay, hello, hello. Good morning. Thank you, Eric. There you go. The man remembers, the man knows. Good morning, Eric. Good to see. Thank you. And anybody else wants to say hello, that'd be helpful. Okay, but yes. Oh, hello. Oh, there's okay. Um, good morning, Francis. Thank you. All right. Awesome. Awesome. Remember, you could submit. Remember this cat. Oh, and there's video too. So remember, he just got tons of points. He said hello. That's a portal. He's showing video. That's a portal for points. And same thing with good morning, Anjali. And oh, and everybody now. All right. Yes. Remember, you could submit even the good morning for points because that's how it works. I didn't have to admit, Eric is very much a point master general. He knows how to get the anyway. That's a compliment. All right. So good morning, Eric. Good morning, Francis. Good morning, Claudia. Good morning, Anjali. Good morning, Tania. Tanaya. Tanaya. Sorry, Tanaya. Good morning. And thank you. And you just got points, total points. Remember to submit because you just used your voice. There's a portal for that for points. Also, you just pointed out gently that I made a mistake. There should be a portal for that. I'm not sure if there is one, but there should be a portal for when I make a mistake. All right, more people are coming. So yes, thank you. And you said good morning. So good morning. And good morning, Sharon. Okay. All right. So thank you guys for doing this for accommodating. Good morning, Billy. All right. Oh, and more people are still coming. We're going to get rolling in a second. I appreciate your flexibility that you're doing this on Zoom this morning. I mean, glad if you got to sleep in a little bit, that's good. But we're also only having half the class, as you know. So the rest of the material I'll post by video. When I do, you'll get more points for watching it. Good morning, Melita. All right. Oh, and more people still coming. All right. And I'm going to tell you right now. So good morning, Billy. Good morning, Melita. Good morning, Matthew. Awesome, awesome. So what we're going to do with this time, I think that because I know Zoom is not the same, I'm going to try to use this time to blast through the rest of homework 2. Because remember, homework 2 was like very long and there has been all this discussion about various, but now I think we're at a point, partly because we've had all these discussions and also because we're on Zoom. I'm just going to now try to blast through the rest of the answers, well, the solutions in homework 2. And then when we meet again, we'll do homework 3, but homework 3 is actually pretty fast. I might even well, we'll see if I can get to homework 3 today, but we'll just try to finish homework 2. So I'm going to try to discuss less and just tell more. So, it'll be more for like, so you could take notes. And obviously, anytime I say an answer or anything that you have a question about, please stop me and ask questions. But other than that, hopefully this will just help us make progress with the material. So, okay. So, whoa, that's not what I meant to do. So we're going to homework 2. Let me just get the thing set up. We're going to homework 2, and I believe that we are up. I believe we've actually finished all the questions in part 1 derivatives. The big takeaway is right here in the middle of the screen, right? I mean, middle of the board. The big takeaway is that from now on, we describe harmonic oscillators with a cosine function that has a phase constant in it, right? Like that's the big, there was also this takeaway about exponential functions. That's a little bit more of a sidebar. To be clear, moving on in the course, and especially in the lab component of the course, we're going to continue to use the cosine way of describing oscillators. We're going to continue to use the cosine way. But from here on in, that cosine function that describes oscillators has a phase constant in it. And okay, I guess I will say this. Why that phase... All right, I think I said this in class, but let me just see if I can say this concisely. Why that phase constant is so important, even though we've somehow gotten away with ignoring it for the first 3 weeks that we were talking about oscillators, that phase constant signify the phi, the extra Greek letter in the cosine argument. That phase constant signifies what point in the cycle the oscillator was when you started your stopwatch, right? Now, in other words, if the phase constant is 0, it means you started your stopwatch when the oscillator was all the way at amplitude position. That's the natural, most convenient thing to do. That's what you did in lab 1. I think that's what you also did in lab 2. That's what the homework 1B assumed, that the motion started, that t equals 0 when the mass was all the way at 15 centimeters from equilibrium, right? That's like the natural. So if you start, if we consider the amplitude position to be the beginning of a cycle, and we consider going all the way from amplitude all the way to negative amplitude and then all the way back, if that is one cycle, right? If that is 2 pi radians to go all the way from one amplitude to the other and all the way back, that is 2 pi radians. That is one cycle. If our stopwatch starts at that amplitude position, then the phase constant in the middle of the page here is 0, right? If the stopwatch starts at any other point, like if we start our stopwatch when the mass is already at equilibrium position, that means we're starting the timing a quarter of the way into the cycle, right? Because one cycle is all the way there and back. 1/2 cycle would be all the way there. So 1/4 cycle would be just halfway there to equilibrium, right? If the phase constant is pi over 2 radians, is a quarter of a cycle, that means we started our stopwatch like a quarter of the way into the cycle. Like that's an example. I'm just reviewing what we said at the end of last class, right? So that phi, that constant in the cosine expression, if it's 0, it means we start our stopwatch at the amplitude position. If it's pi over 2, it means we started when the thing was at equilibrium. If it's pi, it means we started when the thing was at negative amplitude, et cetera, et cetera. That constant signifies what point in the cycle we started our stopwatch. Excuse me, we started collecting data. Now here's, right, and again, stop me, but I believe what I just said was just a review of the end of class last Tuesday. Nobody cares. Nobody cares. We don't need that phase constant. We could call it 0 every single time, and we could do the convenient thing of starting our stopwatch at the beginning of a cycle every time if and only if we only have one oscillator that we're tracking, okay? The phase constant becomes super important. The phase constant, phi, the head start or delay, becomes a super important issue if you have a bunch of oscillators and they're all starting at different places in their cycle, right? Then you can only start your stopwatch when one of them is at an amplitude position, right? If you have a bunch of oscillators that are all starting at different places in the cycle, then each one of them has to be described with some kind of phase constant because they're all at different places in the phase, in the cycle. Why am I saying all of this before I go on? Because what I want you to know, since you're progressing in labs, is taking a whole bunch of oscillators, putting them next to each other and having them all be identical in all respects except for the phase constant. So let me say that again. Taking a bunch of oscillators, a bunch of identical oscillators, like a bunch of oscillators that have the same K, that have the same M, have the same amplitude, and have the same omega. If you have, sorry, I don't want to get germs through the Zoom. If you have a bunch of oscillators that are identical in all respects, but are staggered by phase, staggered at where they are in the cycles, then what that is a wave. What you're seeing in lab 3, and you might want to tell me in the chat, I believe you're up to lab 3 now. I'm hoping that you don't have a full formal report yet due in lab 3. Tell me if you do, but I believe you're up to lab 3 now. Lab 3 brings us into wave motion, right? Wave motion is the next topic. It's a really, really big topic. What I just want to say right here is what you're trying, and lab 3 at first is very intimidating and very it's a big lab. And it's confusing at first and all that, and there's a lot going on, and then there's all the analysis and everything. the key thing that's happening in lab 3 is what you're trying to show yourself is that what a wave is, what wave motion is a collection of identical oscillators all staggered in phase by a constant amount. In other words, waves are made up of many, many oscillators. One oscillator is not a wave. Nothing we've been saying in lectures so far is about waves. Everything we've been saying in the lecture is about oscillators. What you're seeing in lab 3 and where we're heading with this topic is that if you put a bunch of oscillators together, you get a wave. Or put one last final way, and then I'll move on. What you're trying to see in lab 3 is that what a wave is a bunch is cosine oscillation in time superposed onto cosine oscillation in space. A wave is more than one harmonic oscillation happening together at the same time. And the various oscillations are staggered by phase constants. So the phase constant is what allows us to transition from oscillation to waves. I'll say it one last time, and then I'll look in the chat. I'm saying an oscillation is not a wave, but a wave is a bunch of oscillations. Like all rectangles are not squares, but all squares are rectangles. You can have an oscillation without a wave. That's what we've been studying in class so far. But you can't make a wave without a bunch of oscillations. So oscillations, harmonic oscillations, are the building blocks to waves. And the glue between the building blocks is the phase constant. That's like, so again, that's just like whatever, the overview of the course or that. So, and if you're struggling with lab 3, I totally get it. It is hard at first. Hopefully the more of this math we do, the more it'll bring together what's happening in lab 3. But lab 3 is how the point of it is putting together oscillations to make waves, or really in the lab, it's the other way around. In the lab, you're looking at waves and seeing how they're formed from oscillations. In class, we're going to go the other direction. So by the end, it'll all gel together, hopefully for you. Okay, I see something in the chat, so that's good. But I'm going to move on back. So that's all overview. I'm going to answer whatever questions. And if you do have questions about the lab, I'm happy to answer them, although depending on the timing. But other than that, after I look in the chat, I'm going to go just back to homework 2 and just keep grinding through the math. So you have the math. Okay, chat. Oh, yes. Oh, okay, cool. Thank you, Eric. Awesome. See, that's more points for Eric right there. Not that it's a competition, but if it were, he might be winning. What did I say? I did not say that. Okay. So, but all right. So I'm going to go. So just back to the homework 2 again, because I know it's like hard to have a real discussion in Zoom. So we're just going to grind through.
Can I ask a quick question?
Oh, yes, please. Yeah, sorry. Yes. Hi, Melita. Yes.
On the first page before you have something, what's that like symbol? Like the half circle?
Wait. Sorry. You're sorry. On this page. Oh, what's the symbol after the cosine omega? Wait.
No, on the very top, there's like a half circle and then the F. Is a half circle signifying anything or no?
Oh, wait, there's a half circle and then an F. Wait, I think it's probably not. You mean, wait, you don't mean, wait, you mean, wait. There's a half circle and then the F? Oh, wait, you mean just that? Wait, sorry, where
Like above the omega. There's like, oh, it's changed. Now it's a line. So it's one F.
Oh, it just says IF. Oh, I'm sorry. Yeah.
Oh, okay.
Oh, I'm sorry. I see what you're saying. Oh, yeah. What I'm trying to say there. Okay. And I forget sometimes that we don't meet on Zoom a lot. So like yeah. Okay. It says if differential equation, blah, 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 then Z equals Z, da, da, da. So that's just a review of where we are so far. I'm just saying the big lesson of the class right now is if some situation is described by that differential equation, then that means that cosine is the solution to that differential equation. If
Okay.
variable Z can be described by that differential equation, then Z is oscillating harmonically, cosinusoidally in time. Does that?
Yeah, that makes sense. Thank you.
Okay.
Sorry.
No problem. No, thank you. All right, wait. I'm looking. There's something else in the chat. Okay. Sorry. All right. Fair enough. Yeah, I forget that I mean, right. Yeah. No. So it just said IF. Anything in blue is just like weird data about today is just weirdness, but anything in black is supposedly where we are right now. But and yes, and thank you guys. I forget that I don't do this every day with you, but as long as we're looking at this screen, which is a good idea, also so that you know the if then that's in the black circle, that's where I feel like we are now in the course. Like in principle, that is a summary of where we landed last Tuesday. Like in principle, we all know what's in the top black circle, the if then. I'm not saying it's easy, but that's what we're using right now in the course. But just to be clear, as long as everybody is taking this seriously, the circle underneath it where it says A dot B doesn't equal A cross B. So with that, I don't expect you to know that yet. That is the takeaway from the end of homework 2 that hopefully I'm about to get to. Like that's where I'm trying to go, like today. So I don't expect that to be clear yet. That's the goal of where I want to get to by the end of homework 2, which certainly means I should start going now because we have 1 hour left. So, right. So that's what, okay. So the first equation is like where we are, and the second equation is going. Okay. And someone's coming. So I'm going to go back to homework 2. But yes, keep these questions coming, please. Again, because I know it's whatever. Yeah. So homework 2 continued. Now, I think we did all of part Roman numeral 1. I think we did all the derivatives. So now part 2 just says cosine functions. And in a way, this is just plug and chug. I mean, in a way, these are just exercises to make sure that we can picture how cosines work, because from now on, cosines are how we describe harmonic oscillators. But you'll just notice, I mean, it's not a brilliantly written set of exercises, but really it's meant to compare. It's really about sort of comparing what your answers are to A versus B loosely, because it's meant to just show you how that extra phase constant is functioning in the function. That's the point of this, but it's basically just practice. So I'm just gonna do it. I'm not doing the 5-step method. I'm just gonna write down answers that I think make sense, and you stop me if you don't like the answers or you have questions about them. Okay, but if they're clear to everybody and and if you haven't done this homework yet, then you still have to do the solution. You have to show your work, but this maybe will help you. Okay, so I'm not doing diagrams or anything. I'm just like plugging a chunk. Okay, in fact, I'm going to say that in case anybody just tunes in right now. Just in case if you're looking at notes later. Okay, so here we go. Okay. Because I'm about to turn the page. I'm just gonna let this sink in for a second. So, right, the key to what I'm doing right now is just I'm picturing 2 things. One, I'm picturing sine of 0 is 0 always. Therefore, cosine of 0 is 1, right? In my mind, that those are anchors. Sine of 0 is 0. Therefore, cosine is the other one. Cosine of 0 is 1. And I'm picturing in my mind the unit circle. I love the unit circle. Remember, the key to the whole unit, well, the unit circle is a circle of radius 1, right? And cosine are the x values and y sine are the y values. So in my mind, if the cosine of 0 is 1, when time equals 0, the value of the cosine will be 1. So the value of this whole function will be 4, the amplitude. You see, like 4 is the highest value this thing ever reaches. Okay, I'm over explaining this, but that's my answer for, just stop me if you don't understand or don't like it. Then number 2 was asking me to go backwards, 2 values of time for which x equals 0, which would really mean if this is an oscillator, right? They're asking what are the 2 times when x is at the midpoint, at the equilibrium position, right? In other words, when it's at halfway through its cycle. So I think, looking at this thing, I think the whole, well, how can I put this? Well, yeah, right. So basically just that, what I'm just saying on the paper, that when the cosine reaches 0 when the angle is pi over 2. Okay, I'm over explaining this. This is just what I said 2 minutes ago. Like the cosine is 0 when you're at the equilibrium position. So the 2 times that happens here is when the time is 1/2 or the time is 3/2. I'm gonna stop me if you want me to go back a page or explain that more. But then 3, 2 values of t for which x equals 4. So the 2 values of time, so when we're back at an amplitude position. So we're really trying to figure out the period of all of this. I guess I'll show you 2 ways to do this. One way you can just do this is we want 4 to equal 4 cosine pi over t, right? We're looking for times when x equals 4. So I'm plugging in 4 for x. Right. So we're looking, so pi over t equals the arc cosine of 1. That means we want the angle which returns a cosine value of 1. In other words, when is the cosine 1? Well, cosine of 0 is 1. That's certainly one value. But then if you go around a full cycle all the way back to 0 again, if you wait 2 pi later, that's another place where the cosine equals 1. If you go around the unit circle, right? So pi over t equals 0 or 2 pi. Therefore, t equals 0 over pi or 2 pi over pi. In other words, t equals 0, 2. Like that's that's a slightly trickier one than the other. So I'm just looking at, but there doesn't seem to be anything in the chat. Okay, hold on, I'm just changing the video. But another way to see that may be, in fact, even more illuminating. Like what that seems to suggest, like if you back up and think of this as physics, like we're trying to do this math so that we understand the physics. It's asking what are 2 times when x is at the amplitude position, right? It's really asking, the question is asking, when is x at the amplitude position, right? Because 4 is x naught. I could tell that by the way the function's written. X equals 4 cosine omega t, right? So 4 is the highest value that, and the initial value that x ever achieves. So really what this thing is asking is, so what the question's really asking is, what is the period for this simple harmonic oscillator, right? It's asking how how much time does it take? Like, we know the oscillator is going to be at the amplitude position when t equals 0 because phi equals 0. The thing I just explained 2 minutes ago. We know the thing is going to start off at x equals 4. I'm going to write this here. Again, you can tell me to go back a page if you want, but.
Can you go back a page for a
Sorry.
second?
Yeah,
Sorry.
yes, no, absolutely. Yes.
What's SHO?
Okay. Simple harmonic oscillator.
Oh, sorry.
No,
Okay,
no,
thanks.
no. I'm glad you asked because I do tend to do that a lot from here on in. Yeah. From here on in, if I ever write SHO, I mean simple harmonic oscillator. And if I ever write diff EQ, like DIF-EQ, I mean differential equation. So yeah, and as long as you just asked everybody, like even if you, so Melina just asked what is SHO, and I'm saying simple harmonic oscillator. But from now on, pretty much in this whole course, like everything is based on or built from simple harmonic oscillators. So I want you all to remember two things about a simple harmonic oscillator. A simple harmonic oscillator is any system that mathematically behaves like a mass on a spring. Okay, so again, I know I've said this before, but I want to keep the reason we've spent so long on masses on springs is that we believe there's a wide array of systems in nature that all behave like masses on springs, and masses on springs are like the easiest, most vivid versions to picture. So, like, we believe that bobs on pendulum strings behave like masses on springs, but we also believe that every single bit of your long spring that you're shaking up and down in lab 3, what we're really believing is that, like, every bit of that long string, like, that thing was a spring, but it could have been a string, if you know what I'm saying. Like, that long piece of metal that you were shaking up and down, what we're believing from here on in is that, like, every little bit of that metal that was going up and down when you were shaking it was going up and down in the manner of a mass on a spring. And we believe that when you go to PChem next semester or whatever, when you take PChem and you look at atomic quantum systems that obey the Schrodinger equation, that we believe that they are all behaving subatomically or atomically like little masses on springs. And we believe that circuits that we're going to look at later in the semester behave like masses on springs. So again, but the mass spring system is like this fundamental building block for all of these systems in nature, including the fundamental ingredient for all of these waves in nature. And this ingredient is called the harmonic oscillator. So number one, every time I say SHO from now on, I mean something that behaves like a mass on a spring, that obeys all of the math and all of the energy conservation and all the differential equation, blah, 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 and all the cosine stuff that we're looking at right now of a mass on a spring. But the other thing, as long as I'm, like, answering Melita's question, the other thing is the key to a harmonic oscillator. I know I've said it on the board, but let me say it again right now. The key to being a mass on a spring is that we have a frequency, a rate of cycling, an omega. Like, if you're a mass on a spring, if you're a harmonic oscillator, you are cycling, you're going back and forth and back and forth. If you're doing it harmonically, it means that the rate at which you go back and forth, the omega, and therefore the F, and therefore the capital T, like the angular frequency, the standard frequency, and the period, we believe that that constant rate is independent of amplitude. That is truly the key hallmark to a harmonic oscillator, to an SHO, is that, for example, this thing that we're looking at right here, to go back to the homework, right? This x equals 4 cosine omega t. That is a SHO. That's a harmonic oscillator. Its amplitude is 4. 4 is the place, right? Because 4 is the value of x when t equals 0. 4, like, if we were to write this out, like 4 is x naught. 4 is where this thing was originally. I can tell because of the way it's written. 4 is the amplitude. And pi, okay, I'll just, like, this is the amplitude. If you write an oscillator this way, and this is the omega, the angular frequency, right? The rate at which, and I'm about to use it in the thing that I was about to say, that's the rate at which this thing cycles. And the key to a harmonic oscillator is notice those two constants that sort of define it, that characterize it. Those two constants, amplitude and angular frequency, they're at different places in the function, and one is not at all based on the other. They are independent of each other. That is a deep key characteristic of the harmonic oscillator, that the rate at which it goes back and forth in time has nothing to do with how widely spread out it is set up in space. Okay, if you've heard me say, if you're like, he said that a million times, yes, you're correct. So you're getting a big point in the course if you've heard me say that a million times. Excuse me. So anytime I write SHO, I'm trying to pack all that meaning into those 3 letters. That I'm asking you to picture a mass spring system for which the cycling rate in time is independent of the configuration in space. So that these exercises that we're doing right here are just really, we're just trying to play with the meaning of those numbers and see. So like, I just answered question 3, find 2 values of t for which x equals 4. And I just plugged and chugged and sort of did, math backwards. I did cosine backwards. But if I try to think about it physically, what it's really asking, question 3 is really asking, like, when can we expect to find the mass at its amplitude position? When can we expect to find it back where it started at its maximum displacement from equilibrium? So in a way, what this question is really secretly asking is, like, how much time does this thing take to go all the way there and come back? It's really asking, what's the period, capital T, for this simple harmonic oscillator? Right? So if I thought about it that way, I'm doing this. I'm trying to remind you. I'm just trying right now to remind you or review or do an example of the thing we said 2 weeks ago, that any oscillator can be described by its angular frequency, which is radians per second. But from angular frequency, radians per second, you can get standard frequency, which is cycles per second. And from the F, and from standard frequency, you can get period, which is seconds per cycle. If you know one of those 3, you automatically know the other 2. Those 3 things, angular frequency, standard frequency, and period, are 3 interchangeable ways to describe the cycling rate of an oscillator. If you know one, you automatically know the other 2. So again, like we said, 3, so you can convert, and the conversion factor really for all of them, the key conversion to the whole thing is that for every 1 cycle, there is 2 pi radians. Right? So again, the whole reason we have all those 3 is that 1, angular frequency, directly comes from and fuels the mathematics. And the other, on the other side, period, directly comes from and is used in the experimental data. So period is the easiest to observe, to measure, to picture in your mind. Angular frequency is the easiest to do explicitly with the math. And the bridge between the 2 is standard frequency, right? So it all depends on context, which one we're using, but each one gets the other 2, blah, 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 blah. So how do you navigate back and forth between the way I just wrote here? Omega, number of radians per second, is 2 pi radians per every second of the cycle. Omega always equals 2 pi over t. So I'm just saying, if we were to do a check here on what t is 2 pi over omega. And what is omega in this example? We just said omega in this example happens to be pi. right? So apparently, so here, I'm just saying, here, apparently the period of this thing is 2 seconds. I'm saying the mere fact, I think we did this once in class, like just as like a vocal exercise, like some of you, like Jonathan and Eric, and some people were just like answering me as I just shouted out in the middle of class. Like, I'm just saying this as a check. If I know what I'm doing, if I'm trying to translate the physics of this mathematical function, the fact that that pi, oh, sorry, does someone have their hand up? Wait, I'm back and forth between the, oh no, okay. I'm trying to look at both screens at once. That pi that's written in the cosine function, that pi is the angular frequency. It's saying in English, this function is this mass, if this is a mass on a spring, it's starting at position 4. It's going back and forth between 4 and -4, 4 and -4, -4, and it's doing it at a rate of pi radians per second. Literally, right? That's what that pi means. It's telling me that the angular frequency is pi radians per second. What does that mean in English? It means a half a cycle per second. That's what that pi means, because there's 2 pi radians in every cycle. So this thing is saying that this oscillator is going, like, I'm trying to say that just by looking at the mathematical function, you can suddenly picture all of the physics, like once you get used to it. So this is an oscillator that's going back and forth between 4 and -4, 4 and -4, and it's doing so at a rate of a half cycle per every second, a half cycle, because 2 pi radians are a full cycle. So if it's doing a half cycle every second, that means it takes 2 full seconds to do a full cycle, right? That's what I mean. This is just a check. So it checks. It checks with my mathematical answer that two of the times at which this oscillator can be found at the position 4, 2 times are 0 and 2 at the beginning of one cycle and at the end of that one cycle. And if you're getting what I'm saying, you can imagine that the next time it's going to be at x equals 4 is at 4 seconds, and then 6 seconds, 8, etc. You see, so hopefully you just see that it checks that this all sort of makes sense. I will keep going. I'm just looking at the chat. Right. It doesn't look like there's anything in the chat, so I'm going to keep going. Okay.
How's the question?
Oh, please. Yeah, because I feel like, yes, please. Sorry. Yes.
How do you get just seconds and not radians per second? So like, how does the unit work?
Wait, sorry. Say that one more time. How do you?
For the period, how does the unit work that you just get seconds?
Oh, yeah. Good question. Okay. Because, okay. I'll do it on the next page. Very good question. Okay. Okay. Sorry. Okay. So it's a very good question. I'm going to answer it now. I just wanted to write that down. And again, well, so the answer to Melita's very good question is the reason the units work is that the conversion factor here is that there's 2 pi radians per every cycle. So if we convert from radians per second, if we're converting from omega all the way to t, we're converting all the way from radians per second to seconds per cycle. The reason the radians like went away or got canceled out is because it's like one step along the way, we divided out by 2 pi radians per cycle. I mean, so the answer is what I wrote right here, but what I'm trying to say is, yeah, omega is in radians per second, capital T is in seconds per cycle, and we got there by going through F, which is cycles per second.
Thank you.
Does that, sorry, but
Yeah, that makes sense.
it really does. Okay. All right.
Yeah,
Sorry.
I just couldn't visualize it before, but this is really helpful. Thank you.
Okay. No, cool. All right. And to everybody again that too, because no, this tripped me up forever. I mean, honestly, again, for whatever it's worth, I literally remember. I mean, this is not true of everything in physics for me, guys, but certain things in physics, like omega equals 2 pi f, I honestly remember memorizing that for a college physics course. I remember the days when I was like, I had no idea what it meant, but it kept coming up. So I just memorized it. Like I remember like, oh, it keeps coming up that I have to go back and forth between omega and f. So I remember, I could picture the page in the book at the time. I memorized omega equals 2 pi over f, and I used it for a while. And then I remember the day when it suddenly hit me like, oh, 2 pi. Oh, like, and that's just to say nothing is obvious until it is, if you know what I mean. Like, but for all of you, what I'm saying is there's like a bunch of different things that all seem jumbled together. There's angular frequency, there's standard frequency, there's period. It all just seems like this mess, but the hook behind the whole thing is, first of all, the whole thing is, yes, there's 3 different ways to measure the same thing. They're for different contexts, but they all mean the same thing. And number 2, the hook behind all of them is that there are 2 pi radians to every cycle. I mean, but anyway, so I'm glad Melita asked that, because anyway, okay. Okay, so back to but keep it come again. I hope everybody's, all this homework and stuff, it's just an excuse to get questions like that. Like, if all day I just answered questions like that, it would be more productive than whatever it is I'm trying to get through. That's my opinion. So never feel like you're getting off the topic by asking these things. They are the things. Okay. But anyway, back to, so number 4 now. Okay. Number 4. Okay. So find a value of T. So the question is T such that, okay, I'm going to say another side note. You notice, like, I'm intentionally trying to not do the 5-step method just to save time. And because I know it's driving people crazy that we've been like sitting on homework 2 for weeks. So I am trying to move forward. But you ever notice, like, if I actually did do the 5-step method, it actually makes what I'm talking about a lot more clear. I don't know if anybody's, but that's why you're supposed to do it in the homework. It actually makes it more clear. But anyway, all right, but I'm not doing it. So, find a value of T for which X equals -4. Okay, like that's the question. T such that X equals -4. Well, there's various mathematical ways I could do this. But if I am picturing the spring now, the way I'm trying to ask you to picture it, if I now see what's going on and I see the period and I see the frequency, it seems to me that the answer is just T equals 1 second. Now I'm just saying that. Like, why? Because capital T equals 2 seconds. So we're talking here about a half. I'm saying in English, it's asking when is the thing at its negative amplitude position. That means it's asking like how much time elapses before we do a half cycle, before we go all the way there, but not yet all the way back. So if I've just figured out that the cycle takes 2 seconds, half of that is 1 second. Now, that's what I think the answer is. There's other more rigorous ways you could do this. So please stop me if that doesn't make sense. Well, I mean, but here's a proof, I guess, no, I'm going to go on Because the way I could prove that, I could do it the long way, but the long way is exactly what I'm going to do for number 5 now. So if number 5 works for you, then you could go back, and you didn't like number 4, you can go back and do number 4 this way. Because number 5 says find t such that x equals 2. Now I'm going to do this one the long way. And the reason is this, and this is actually almost interesting. Like, I know that this thing is oscillating back and forth between +4 and -4. So now it's asking, okay, so when is it at 2? So it might be tempting, since I'm being all like logical and physical about these up until now, I'm looking for shortcuts. We're always looking for shortcuts. It might be tempting to look for a shortcut and say, oh, well, now we're asking for like half the distance. So isn't the answer half the time? You might think that, like, I'm not asking for x equals 4. I already got the answer for that. I'm asking for x equals 2 now. So you might say, okay, half the distance, half the time. But that would only be true if distance was directly proportional to time. If distance were a linear function of time. Our whole thing here is that it's not a linear function, it's a cosine function. So you can't, it's not directly proportional. That's the essence of cosine. It's curved, not straight. So I actually do have to think this through. I don't know if that makes any sense or not, but like, yes, we always want the shortest cut that we can do, but that's a shortcut that won't work here. So I'm going to do it the long way, which I kind of did before. I'm going to say, all right, remember, the equation that was given, the position function that we're dealing with is x equals 4 cosine pi over t. We're looking for t such that x equals 2. So I plug in 2 for x. I say, okay, 2 equals 4 cosine of pi t, right? So I divide both sides by 4. So I say, okay, 1/2 equals cosine of pi t. I'm going to go to the next page. So tell me if you want me to go back. Okay. I'm just rewriting that. 1/2 equals cosine of pi t, right? I'm looking for the t such that the cosine of pi times it equals 1/2. So I'm saying that pi t equals the arc cosine, the inverse cosine of 1/2. That may sound intimidating.
Sorry, is there any chance you could go back
No,
for
I
a
know.
second
I
once
was
you're done?
hoping you would. I actually wasn't believing that. Yes, sorry, absolutely. I'll pause for yes. Sorry. That's major points. She's in a point competition with Eric. It's not a competition. Stop saying competition and stop talking to yourself. Okay, I'll stop talking to myself. Okay.
Okay, got it. Thank you.
No, thank you. And the other people in the room also thank Melita, because somebody benefited from that, but they had to have her do the dirty work of actually saying something. So blah, blah, blah. All right. Okay, so pi t equals arc cosine of 1/2. That may sound intimidating, but first of all, it does mean just on your calculator. Oh, and by the way, for all of this, your calculators for this that we're doing right now, your calculators should be in radian mode. This is all assuming radians now, not degrees, right? But if you got on your calculator, you just typed in 1/2 and then hit inverse cosine to the -1, it would spit out a number. The thing is, I think I know what that number is. I need the angle such that the cosine is 1/2. I happen to know that that is what we would call 60 degrees, or in other words, pi over 3, right? Because pi is 100. How do I know that? Because 180 degrees is a half cycle, or 360 no scope is a full cycle. So 360 is 2 pi. So 60 degrees is pi over 3. How do I know that the cosine of 60 is 1/2? I'll totally admit, I'm just used to that. I mean, it's on the unit circle. You could get it on the unit circle. But at that point, I've just used it enough that, yes, that one is just memorized by accident in my mind, that the cosine of 60 is 1/2. Is there a way that I really remember? I mean, really, honestly, the way I know that is that I know that the sine of 30 is 1/2. I sort of base everything in my mind on sines because sine is super, cosine's crappy, right? So, cosine's counterintuitive. I know that the sine of 0 is 0, and then I know that you go up a little bit, sine of 30 is 1/2. That's just in my, for whatever it's worth. Okay, so then I know if the sine of 30 is 1/2, then the cosine of 60 has to be 1/2. I don't know if that helps anybody or not, but you have calculators for that too. So anyway, but that means pi over 3 radians. So pi t equals pi over 3 radians. Therefore, t equals 1/3 second. All right, that's the answer. Now, that one is not obvious, but I think it's true. And by the way, let's even think about that for a minute. I'm literally saying I'm just, again, I can't believe the amount of time I have not saved by not drawing the original diagram. I mean, I really should have drawn the original diagram. This is all going back to homework 1 now, right? It's just that now we're feeling like we can describe all of what happened in homework 1 with cosine functions. So at the beginning, this thing was at position 4. We decided that 1/2 of a second into its motion, it ended up at the middle at x equals 0. Then at 1 second, it was on the other side. At 2 seconds, it was back to the beginning. So when was it at x equals 2? This was like a question in homework 1B, just we didn't have cosines then. When was it at position 2, halfway between 4 and 0? It wasn't there at a quarter of a second. It was there at a third of a second. It was, right? You see the pattern? Like the fraction is reasonable. The fraction 1/3 of a second is somewhere in between 0 and 1. But it's not midway between because this is not a linear function. It's a cosine function. All right. Anyway, that's the answer of 1/3 second. So we're almost done with this. And what? Okay. And then 6 says, what's the maximum value? What is x max? Well, we don't know this at this point. I mean, the answer is x equals 4. The maximum is 4 because that's the amplitude because cosine never gets greater than 1. Therefore, the whole function never gets greater than 4. I can't. So x naught equals the initial and the maximum. In other words, x naught is the same thing as amplitude. So that's it for those. Then we're just going to do, now we're going to do 3 more exercises. B, and again, you could stop me or bring it back. But B now takes the function and it goes like this. So we're just doing a comparison now. Just, sorry, this table's so squeaky. We took the function, we took the function from part A and we just tweaked 2 things. We tweaked the angular frequency and we tweaked the phase constant. Right. And we just want to be able to see that in action here. We're saying this oscillator now is going twice as fast as the other one, right? The other one's like here, in other words, here, omega is not pi, it's 2 pi. And that means it's doing 2 pi radians per second. That means this one's doing 1 full cycle per second. The other one did a half a cycle per second. This one's doing 1 cycle per second, right? F equals 1 cycle per second, or in other words, 1 hertz. And the period for this one, therefore, is 1 second per cycle. Whereas the other one was 2 seconds per cycle. You see what I'm saying? I'm just like looking at it right away. I can tell that. So this one is taking half as long to complete a cycle as the other one because it's cycling twice as quickly. Like just right away, I can see that in the function. Also, here this time, phi doesn't equal 0. It doesn't equal 0. This time it equals pi over 2. So this one, when I started my stopwatch, the mass was already at the equilibrium position, or vice versa, if you like. Like this one didn't start at the edge, it started at equilibrium position. That's what that means, right? And again, that's just an example. Phi could be anything. It could be 0, it could be pi over 2, as we keep using the example, or it could be pi, or it could be pi over 3, or it could be whatever. But anyway, so now we're just plugging in and seeing how the answers compare. So when t equals 0, what's the value of x? I think right away I know. I think the value of x is 0. Just eyeballing this, because I know that the phi is pi over 2. I believe that means that this thing started at equilibrium position right from the beginning, but I can check. I believe that's right, but I'll check. When t equals, so x equals 4 cosine 2 pi 0 plus pi over 2. And I'm just plugging in 0 for t. So x equals 4 cosine 0 plus pi over 2. So x equals 4 cosine of pi over 2. And cosine of pi over 2 is 0. So yes, it checks. I hope that's clear. I'm going to go to the next page now. Well, no, okay. And again, I think I can just use my eyeballs for this. Find a value of t for which x equals 4. Well, this thing still has the same amplitude. Oh, but it did. Oh, it has the same amplitude, but it has different base. So this one, I guess I won't eyeball this. Oh, well, 9 is circular. 9. All right. Anyway, I'm going to do this one. So,
Sorry to
sorry.
do
Yeah,
this
no, you're
again.
right. No, you're
Thank
right.
you.
No, yeah. No, you're right.
Thank you.
No problem. Okay. Yeah. So 8, again, we're using this function. We're using, so the question is, what is t such that x equals 4? And it's just asking for one value. So, okay. So 4 equals 4 cosine of 2 pi t plus pi over 2. So, right, I'm looking for t here, right? So I divide both sides by 4. So I could say 1 equals cosine of 2 pi t plus pi over 2. Um, uh, so sorry. So 2 pi t plus pi over 2 equals arc cosine of 1. And we know that the arc cosine of 1, that means what is the angle such that its cosine is 1? Well, that means 0. Like you could do that on your calculator, but the cosine of 0 is 1. Therefore, the arc cosine of 1 is 0. So 2 pi t plus pi over 2 equals 0. So 2 pi t equals negative pi over 2. So so 2t equals negative 1/2. So t, ooh, that's a problem. Wait a minute, one sec. Where'd I get the negative? Oh, that's interesting. Hold on one second. Oh, well, this is true, but it's not the easiest answer I'm looking for. Okay. I think for a second. Okay. Okay, let me explain what I just did. I'm saying the answer is 3/4 of a second. Okay, I'm saying the answer is 3/4 of a second. Now, where did I get that? Maybe that's a little tricky. The math gave me an answer of t equals negative 1/4. Negative 1/4. Now, that's a negative. That's weird because we're talking about time. It's not wrong. It's just not what I'm looking for, right? Like everything in the math means something physically. It just all depends on what physical question you're asking. What this thing is saying is that the lowest, the most obvious moment in time when the mass would be at position X, the most obvious moment, right? Oh, this makes total sense. Yes, this does make total sense. It's saying the most obvious moment when the mass is at amplitude position at X equals 4, it's saying is at negative 1/4. Now that seems weird. What does negative 1/4 mean? Well, it means 1/4 of a second before I started my stopwatch, right? And that right there, that makes sense because that's what we're saying. Like the reason we actually had to do a lot of math right here is because we already said the phase constant is pi over 2. The phase constant is telling us that we didn't start our stopwatch when the thing was at amplitude. We waited until it was at equilibrium to start our stopwatch. And remember, for this oscillator, we know the period is 1. It takes 1 second to go all the way there and all the way back. So by waiting until it was at the equilibrium position, we waited a quarter of a cycle. We waited a quarter of a second. What the math is telling us is actually something totally logical and totally that checks out with everything else. It's saying the first time this thing was at an amplitude position was a quarter of a second before you even started timing, Yaverbaum. Like you didn't even, right? It was there and you waited a quarter of a second to start your timer, and then it was at the equilibrium position. So the math is accurate, sort of, I think, excitingly accurate when the math says, if you want a time when this thing was at amplitude, go back in time a quarter of a second before you even started timing, and that would be right, and it is right. However, of course, that's not what I'm looking for here. Like, I wasn't even timing then. That's not part of my experiment. I want a positive time, of course, to answer this question. So what do I do to get remember, there's an infinite number of times that this thing is going to be at X equals 4, but if I want the first one or the simplest one to picture in my experiment, what I have to do is add literally 1 to the answer that it gave me. I'm adding 1 to it. Why am I adding 1? Because the period for this oscillator is 1. We already figured that out. Like, I'm not saying I would always add 1. I'm adding 1 for this case because its period is 1. If it was at X equals 4 a quarter of a second ago, then it would be at if it was at X equals 4, if it was at amplitude position at negative 1/4, then it'll be there again 1 full second later from negative 1/4. So negative 1/4 plus 1 equals 3/4. And that's my answer. it's 3/4. It's a funny number because the phase constant is not zero. It's pi over 2. In a way, that's exciting how that all works out to me, but I don't know if that's, I'm looking in the chat to see, but if that's clear, good. If it's not, put something in the chat, but that's the answer. I mean, that's one possible answer. There's an infinite, it'd be that plus one. In other words, if you're understanding what I'm saying, then it'll be there again at 7/4, and it'll be there again at 11/4 of a second, et cetera, et cetera. Every next second, it'll be there again, but that's the simplest answer. Okay. That ends the cosine practice. Now, in homework 2, I'm going to do, we only have 10 minutes, I know. This is looks like a lot here. I mean, it is a lot. The key piece of knowledge in all of this is what it says right there under assume. Oh, wait, sorry, you can't see my screen right now. Hold on, I'm going to, okay. The key piece of knowledge here is where, or the key two piece of knowledge is where it says assume. Oh, wait, well, let me see if I can. Yeah. The key thing here, even if we don't get to all these exercises, is the different ways that you could do multiplication when vectors are involved. Now, this seems like a totally different topic. It is kind of a different topic. We've talked about some of this when we were defining work as a integral of a dot product of force with displacement. It turns out that dot product, that cosine thing that we've said, is one of a number of different ways that multiplication can occur in a vector context. I think the best thing I can do with the next 8 minutes is, no, I guess I'll give, okay, I'll give, hold on, let me just think for 1 second. Yeah, actually, okay, no, the best thing I can do is give a summary of this concept, and then I'll try to bang through answers, but I think it's better that I give a summary than give the answers. Because again, if you've never done this homework yet, you still can if I give you a summary right now. So all right, so we're going to go back to the screen here. Oh, I got to share the other screen. Oh, sorry. Okay. Okay. Since I know we have like 5 minutes left, here's my summary of what's going on. And we'll go back to the answers and everything next week. When you have vectors, when vectors are involved in your thoughts, there's 3 different ways that multiplication can occur. First way is that a vector can always be multiplied by a scalar. And remember, scalar is just a pure number, just a pure size of a vector. A vector has size and direction. If you multiply a vector by a pure scalar, you always get a vector, always. When you multiply a vector by a scalar, you're just taking an arrow that has a certain size in a certain direction, and you're changing its size. You're multiplying it by a pure size. So you're taking an arrow and you're either scaling it up or scaling it down. When you so when you multiply a vector by a scalar, you're just changing the size of a vector, and the answer is a new vector of same direction but different size. That's number one. That's scalar vector multiplication. You always get a vector. But then if you have 2 vectors, call them A and B, 2 quantities with magnitude and direction, there's 2 different ways you can multiply them. You can multiply them in a way that that produces a scalar, a pure number, or you can multiply them in a way that produces a vector. The first way is sometimes called the scalar product of 2 vectors, but we use a dot to denote it, so it's also generally known as the dot product. Vector A dotted with vector B gives you a pure number, not a vector, a pure number. And we've said this before, like work is force vector dotted with displacement vector. You get a pure number, and the pure number, the scalar, represents how parallel, how aligned the 2 original vectors were. In other words, you get an answer that doesn't have direction, an answer that indicates or measures how close in direction the 2 original vectors were. The more lined up they are, the closer they are to just being 2 numbers on a number line, the bigger their non-directional product is, right? So the dot product of 2 vectors is the length of one times the length of the other times the cosine of the angle between them, because cosine of 0 is 1. Because the smaller the angle is between them, the bigger the dot product is, because the dot product gets rid of direction. It says the less you guys are differing by direction, the bigger your non-directional, your scalar product will be. So the scalar dot product between 2 vectors is the length of one times the length of the other times the dot product, times the cosine of the angle between them. On the other hand, and I know we have 2 minutes, so this is just the last thing. We'll do the exercise later. On the other hand, there's this thing called the cross product. The cross product between 2 vectors is itself a vector. It's a way of measuring not only the size of 2 vectors, but their directions relative to each other. The more 2 vectors differ in direction, the bigger their cross product is. So, with 1.5 minutes left, the cross product between 2 vectors produces a vector that we can call C. The magnitude of that vector, the size of the answer that you get when you're crossing 2 vectors, the size is the size of one vector times the size of the other times the sine of the angle. It's like the opposite of dot product. It's not a coincidence. It's what you'd expect, because the sine of 0 is 0. So if 2 vectors are lined up and they share the same direction, then direction is not playing a big role in their relationship. So the cross product is 0. The more they differ in direction, the more perpendicular they are, the bigger the magnitude of their cross product is. So there's 1 minute left. So that's why the sine instead of the cosine. The only thing left is, wait, if the cross product between 2 vectors is a vector, then it not only has magnitude, AB sine theta, but it also has direction. What's the direction of the cross product of 2 vectors? I'm going to say this once. We're going to practice it more later. We're going to say it once now just so you have it. The direction of the answer of the cross product between 2 vectors, the direction of that final resulting vector is given by something called the RHR, the right-hand rule. The right-hand rule says, I'm just going to say it once, we'll practice it more later. It says you place your finger of your right hand, you place your fingers along the first vector, you curl them toward the direction of the second vector, and wherever your thumb points, That's the direction of the answer. That sounds totally weird. I know we'll practice it more next week, but the purpose of it is just this. And this is where I'm ending. Okay, I promise. The cross product between two vectors measures how perpendicular the two vectors are. The more perpendicular they are, the greater the sine of their angle, the greater the cross product. So the cross product measures perpendicularity. Therefore, the cross product itself is always perpendicular to both of the two vectors that it's measuring. So the right-hand rule is just a way of keeping positive signs and negative signs straight. It's just saying if you have any two vectors at all, take your fingers, go from one vector, point to the other. Your thumb will stick out in the one and only axis that is perpendicular to both of those original vectors. So the right-hand rule gives you the direction of the final answer. The final answer will be perpendicular to the original two. We didn't need a right-hand rule for the other two processes because the other two processes, well, we didn't need it for the dot product because the dot product doesn't produce a vector. It produces an answer that doesn't have direction, a scalar. But the cross product produces a vector. The magnitude of the vector is AB sine theta. The direction of the vector is given by the right-hand rule. That's my discussion on that. We've gone 1 minute over. Thank you for being so patient for doing Zoom today. I will post a video for the rest or at some point, and then I'll give you points for watching it. But for now, just keep on keeping on with wherever you are in the homework. Thank you so much. And I'll hang out for a minute. For any questions, I'm not going it, but you guys can go. Have a good day. Have a good day. But I'll be here if there's any questions. Okay. Have a good day. Thank you.
We're gonna talk more about this next week, right?
Yes. Yes.
Okay, perfect. Thank you so much. Have a good day.
You too. Thank you. All right. Thank you. Oh, no problem. Thank you both, Billy and Jonathan. No problem. I see the chat. Yeah, no problem, Jonathan. But thank you and thank you both for being here. Okay. Oh, thank you for being here. Okay, cool. But if you have any questions, I can answer them now. Or yeah, no, I'm stopping the recording either way. The recording. Okay. Goodbye. Been a pleasure seeing you.